Hello everyone. Today we are doing section 3.7, mechanical vibrations. I'm trying to use a different way to record my lectures because with cell phone, it's always losing focus and everything is becoming blurry like every 3 seconds and I cannot control it while I'm reading the lecture. It's hard to control what cell phone is doing. So I'm doing it over here. Maybe it's going to work a little bit better, but I'm not sure actually. So we are going to start doing 3.7 mechanical vibrations, and we are going to do motion of a spring, of a mass on a spring. So what is going to be considered? Well, first guys, there are two cases. We are going to start with case one. Case one is undamped free vibrations. Let me put text here. And so first case. Usually the question is, well, first, what is undamped? Second, what is free? Free of what? Let me kind of explain. Imagine that you have a spring and you attach it to a wall or something like this, and you stretch the spring and put a mass on this spring, mass M. And well, you put some kind of, I don't know, liquid or rollers so to avoid friction. I'm going to draw little wheels over here. This is just like showing that there is no friction. So undamped means no friction. Imagine that we stretch the spring and we kind of do measure position of the mass in direction toward the right. Well, we don't need y-axis here because motion is going to be horizontal, but that's going to be the case. So what is free? Free of what? Well, guys, if you stretch the spring and keep compressing and stretching and compressing and stretching it, that's going to be forced vibrations. So we have free vibrations, means that you stretch the spring and then you release it and then you are not touching it and you are just observing how the system is moving. So the spring is free of external force. So there is no force applied to the system after you changed the initial position. Okay, so what kind of forces are going to work here? Well, we remember that when we do have the spring, there is a Hooke's law, which tells us that if we stretch a spring will try to compress itself in the opposite direction, and this is called Hooke's law. Hooke's law, and it looks like minus kx. What here is minus, what is k, what is x? Well, x is the displacement of a spring from equilibrium position, where the spring is not stretched. So you move it 2 centimeters or 2 meters from equilibrium position, that's going to be x. What is k? Well, it's a stiffness of the spring. You understand that if the spring is kind of made out of thin wire, it's going to be easy to stretch it, and the spring which is made is from something harder is going to be harder to stretch. Like, you know, you have springs under the monster trucks, those springs are going to be hard to stretch, right? Why it's minus? Well, minus shows that the force is going to oppose to displacement of the spring. So if you shift it to the right, for example, the force will try to pull it back to the left. Hooke's force. Right, so we do have Hooke's force and x. I'm going to put over here in parentheses t, it's a position of the mass. Now, let's apply to this situation second Newton's law, which tells us that, I'm so not used to write on a computer. Newton's law tells that acceleration of the mass multiplied by the mass is equal to the net force applied to the mass, right? Net force applied to the mass. In our case, it's a Hooke's force, right? So minus kx. Now we have two kind of variables here. What we do know about the mass is like, we know how much is mass, right? How many kilograms. We do know usually stiffness of the spring, how hard is the spring, right? What is acceleration? Well, if you remember calculus 5C, remember that acceleration, it's a first derivative of velocity or second derivative of position. So I'm going to put instead of acceleration, second derivative of position here, and we are going to have a differential equation, right? Second derivative of position. I'm going to move the Hooke's part to the right side, to the left side of my equation. And I'm going to get perfect second order differential equation, right? Usually, the standard form is going to divide the whole equation by m and have it like this. Second derivative plus k over m by x equals to 0. And we are going to name k over m coefficient of x, which is no number when you have a spring and a mass given, as omega 0 square. You are going to see why do we not just name it omega 0, but we do the square. Let's write it down and try to solve it. We already know how to solve equations like this, right? So I'm going to write down a second derivative plus omega x squared, and that's going to be equal to 0, right? Well, that's a typical second order linear equation with constant coefficients. We solve it using a characteristic equation. So we are writing down r squared plus omega squared equals to 0. From this simple equation, we see that r squared equals minus omega squared, which gives us two complex solutions, r equals plus minus omega 0I, right? Well, do you see why do we have square? When we extract the square root of omega square, we are just going to get omega. We like to deal with something not a square root. That's why we call it omega square here. Okay, now how solution is going to look? A general solution of this equation is going to look like this, C1. Well, because here we don't have any real part, we're going to have the equals to 0 and mu, imaginary part equals to omega 0. We are just going to have sine and cosine. We're not going to have any exponential factor, right? So we are going to have cosine of omega 0t plus C2 sine of omega 0t. That's general solution. So C1 and C2 are constants which are found from initial value problem, right? So I'm going to write down C1 and C2 are defined from initial value problem. Okay, let me scroll it a little bit up, and maybe we should kind of set something up. Well, I'm going to consider one actual problem. We're going to solve it, and then I'm going to explain you how else we can represent this final solution. So let's start with our first example. Example 1. We have a mass m, which equals 0.1 kilograms, and it's stretched from equilibrium position for 5 centimeters. 5 centimeters from equilibrium. The constant of the spring is given as 4.9 newtons and over centimeter. Now, it doesn't look very nice. Actually, it looks like G, right? Everyone is going to see that I think it's G. 4.9 newtons per centimeter. And usually the question is find find x of t. So if we convert it into differential equation, how it's going to look? Well, let's start with the equation itself. We do know the mass, we do know this stiffness of the spring, so I'm just going to write down the second derivative of x plus, well, we do have, let's go back, what is omega? Omega is equal to k over m, so I'm going to copy my k, 4.9 over my m, 0.1, x equals to 0. That's a differential equation, right? They tell us that it was stretched 5 centimeters from equilibrium. They don't tell us direction, so we are kind of free to choose what direction do we move it from equilibrium position. I'm going to draw a picture. Usually it makes sense to draw a picture. Imagine that there was a spring, right? And they stretched it this direction, 5 centimeters from equilibrium position. Also makes sense to draw direction of positive x-axis. It's equilibrium. Okay, positive direction of x-axis here, they are matching. So I'm going to write down that x of 0 equals 5 centimeters. If I put my x-axis in opposite direction, then obviously my initial position is going to be minus 5 centimeters. So pay attention to direction of initial stretch and direction of your x-axis. Well, this is initial value problem, right? Initial value problem, which we are going to solve. This number, well, we already know the solution, right? We're not gonna kind of pretend that we're solving it one more time. So we know that the omega 0 square equals 4.9 over 0.1, which is going to give us 49, from where omega 0 equals 7, right? The square root of 49. Well, I picked the number to not deal with anything complicated or, decimal numbers. So what we have, solution is going to be, x of t is going to be c1 cosine of 7t plus c2 sine of 7t, right? Well, we already know the solution. Solution, general solution is sitting over here. Now we need to find the constants. So what I see is that my initial value problem does not have one more condition, right? I do have position at 0 moment is 5, but I don't have any first derivative. Remember, what is first derivative in physics world? The first derivative in physics world is a velocity, right? So in the problem, they don't tell anywhere that we do have velocity. So I'm going to assume that the first derivative at moment 0 is equal to 0. So the object was not given any initial velocity. I don't have any space here to write. Maybe I'm going to put a text over here. Give me a second, guys. So let me move the text box over here. Yeah. No. Where? No. It's always going to be the case. No, guys, it's not always going to be the case. Sometimes objects are going to have initial velocity. So I'm just going to label it here that we are choosing first derivative equals to 0 because no one in the problem tells us that was any initial velocity. Now I'm just going to use this initial value, substitute them, and find the constants. So x of 0, I'm plugging in 0 instead of t. You know that usually we do give 0 to make our calculation simpler. It's not necessary to give initial conditions at 0, but it's going to be very easy to plug in 0 here and here, right? So we do have cosine of 0 equals to 1 and sine of 0 equals to 0, which gives us c1 right away. So c1 equals 5. X prime of 0. Well, first we'll need to find x prime. It's going to be what? Derivative of cosine is minus sine, c1 sine of 7t multiplied by 7 plus c2 cosine of 7t multiplied by 7. Remember, when we differentiate, don't forget about the compositions that we have cosine and 7t composed. So now we are plugging in 0 into both functions. So this one is 0 and this one is going to be 7c2, right? We do know that no initial velocity was given, so we're going to get that c2 equals to 0, and our final answer is going to be x of t equals 5 cosine of 7t. That's how the object is going to move. So you stretch it and it's going to oscillate as a cosine. Pure cosine with amplitude 5 and the frequency or a circular frequency equals to 7, right? Well, guys, sometimes you are going to get both initial stretch and initial velocity, two initial conditions, and then two constants are going to be present. In physics, we don't like to have too many functions, so I'm going to show you the way to combine these two functions, sine and cosine, with different constants into one. We do learn it in trigonometry, but I'm not sure that everyone kind of remember this. So this is the answer to the problem. Let me check my marker. So if you have expression C1 cosine of, well, I don't know, let's say omega 0t plus C2 sine of omega 0t, you can represent it as one, either sine or cosine, using a special trick we teach in trigonometry. What I'm going to do, I'm going to divide and multiply my expression by square root of C1 square plus C2 square. So whatever multiplied is going to stay here. Divided part is going to belong to each of this first term and the second term. C1 square plus C2 square cosine of omega 0t plus C2 square root of C1 square plus C2 square and the sine of omega 0t. Well, now why I'm doing this? Well, if you remember the formula, let me write it down somewhere separately. Give me a second. The formula, which looks like this. Sine of alpha plus beta equals sine of alpha cosine of beta plus cosine of alpha sine of beta. This, our formula represents a similar situation. Just we do have cosine. Let's consider that beta is like whatever is the first term, this one, right? We do have a sine, right? These two factors can be considered as a sine and cosine of some angle alpha. Why? Well, just imagine that you have a right triangle with sides. Well, we want to have this as a sine, right? So the sides is C1 and C2. And here I'm going to call this angle delta. Well, no matter what are the constants, you can always build a triangle like this. You just like, the constants are 5 and 15. You measure 5 this direction, 15 this direction, make a right triangle, right? For this right triangle, what is going to be sine of delta? Sine of delta is going to be opposite side, which is C1 divided over hypotenuse. What is going to be hypotenuse here? Hypotenuse is C1 square plus C2 square, right? So we're going to have C1 over C1 square plus C2 square. Well, you see that cosine adjacent side is going to be a similar formula just with C2. So we do see that these two fractions can represent sine and cosine of a certain angle delta, which we can always find out by drawing the triangle and taking protractor and just measuring it. Just draw a triangle with constant 1 and constant 2, then take a protractor, measure what is the angle. That's going to give you the angle. Of course, no one is doing triangles actually. People are using trigonometry to calculate it, but normally, why not? So now what I'm going to do, I'm going to rewrite my formula. Let me go back to blue. As a square root of C1 square plus C2 square. And I'm going to write it down as 1 sine. And I'm going to put beta first. I'm going to put omega 0t. And then I'm going to put alpha, which is going to be this, I'm going to put this delta. So my alpha, sorry, is going to be this delta. Well, you see that instead of two functions, we get one function. Sometimes it's a little bit better because it's just easier to draw one sign instead of the sum of sine and cosine. One sign we do know how to draw, right? This is amplitude, this is frequency, this is phase shift, so everything is clear. Usually you have to do this when you do have both constant present. If you have just one constant, it's already either sine or cosine. You don't need to worry about kind of representing it. What else do we need to know about undamped motion? Well, we know that frequency, let me write down the frequency one more time. The frequency is a square root of k over m, right? And I think the period, if you guys remember, the period is 2 pi over frequency, right? The period of the motion, and that's going to be 2 pi, and I'm going to flip this fraction over m over k, which means that heavier mass is going to oscillate with longer period and harder spring is going to oscillate with a shorter period. Okay, well, that's basically all about undamped motion. Maybe I should consider one more example where actually we have both velocity and initial displacement given. Let's consider one more example. Give me a second, guys. I'm going to shift it up. Let me change my color. I'm going to use green. So, example 2. Well, I don't know. Let's imagine that mass equals 2 kilograms was displaced by, has initial displacement of, I don't know, 2 centimeters. And somebody gave it velocity in opposite direction. Velocity, I don't know, let's call it 30 centimeters per second. That was velocity. I'm going to draw the picture because without picture it's hard to understand what is like displacement. So up direction of positive direction of x-axis to the right, and just write down how the differential equation is going to look. Second derivative. Oh, I did not give the spring constant. Let's consider that the spring constant is equal to, I don't know, 100, for example. Newtons per centimeter, okay? Maybe 100, maybe 200. So it's going to be like, I don't want to deal with weird square roots. Let's do 200 newtons per centimeter. So here I have to put k over m, here x equals to 0, and the initial condition x of 0 equals 2 and x minus 30, because we kicked it in opposite direction. We kicked it to the left. Well, I'm going to substitute my numbers into k and m, and I have 200 over here and 2 over here, right? What else? Then x, right, equals to 0. So my omega 0, if I simplify it, it's 100, extract the square root is going to give me 10. Well, I definitely picked up k to make it like equal to 10. Well, I'm going to just write down my solution. Here we are practicing with converting into this form from 2 sine cosine into 1. So my goal is not to solve differential equation, but represent answer at a certain form. So what we have, a general solution x of t is going to look like c1 cosine of 10t plus c2 sine of 10t, right? And we'll need to find c1 and c2 using our initial conditions, right? So x of 0, which we know equals 2, is going to be equal to c1. So we do know that c1 equals 2. X prime of 0, we'll need to differentiate this expression. We already know that c1 equals 2, so you can use it actually. So it's 2, the cosine is going to give us minus sine of 10t by 10. By the way, usually it's a formality, right? You know that the sine at 0 is going to be 0. Plus c2 cosine of 10t multiplied by 10. And if we substitute 0 instead of t here and here, we are going to just get c2 by 10, and it's supposed to be equal 30 with minus, I'm missing minus here. So if I calculate c2, I'm going to get minus 3. So now I'm going to write down my solution with constant c1 and c2. So c1 equals 2, that's 2 cosine of 10t. And c2 equals, I'm sorry, writing down plus, supposed to be minus, minus 3 sine of 10t, right? And now what I'm going to do, I'm going to roll it into the form of 1 sine, right? So I do have my constant 2 and minus 3, so my square root is going to be a square root of 2 squared plus minus 3 squared. And here I'm going to have 2 over 2 squared is 4 minus 3 squared is 9. So we are going to get the square root of 13 here, cosine of 10t minus 3 over square root of 13 sine of 10t. We're almost done with this problem. So square root of 13, right? So we do know that this is sine of some angle and this is cosine. If we divide sine over cosine, we are going to have tangent, right? I'm going to write down somewhere separately. So tangent of delta sine, which is 2 over square root of 13, over cosine. Let me label it, that's a sine of delta. This is cosine of delta. I'm going to use a minus because formula actually has like positive everything. 1 square root of 13 cancels and we have minus 2 over 3. You always can take a calculator, find tangent inverse and actually find the delta, right? So I'm just going to write down over here, I'm going to write down over here just the sine of 10t plus delta, and I'm going to write down the delta is tangent inverse. I cannot have a calculator right now because I'm here on whiteboard. But that's going to be representation of our solution as one formula. Okay, well, kind of that's how we solve everything. Okay, so now let's move to case number 2. Case number 2 is going to be, let me scroll it up. It's going to be more complicated. It's going to be damp free vibration. Let me use text. And I want to kind of write a long sentence. I have to write down 2. Okay, now what is what here? What is damped? Means that there is some friction. Damped means friction. Free, no external force. Well, what is typical example of damped free vibration is just a very safe same problem, but you have friction as a normal life. You cannot avoid any friction between the mass and any desk or table or whatever. I'm going to do a slightly different picture because, well, it's kind of explaining the point. There's a spring on the mass, so it's on the spring. Imagine that we put it in a bucket of water, or just like a big can of water. Well, it can be water, it can be any other liquid. Let's imagine that's water. Well, what do we have in water? In water, we do have the force which resists the motion. Like if something is moving, for example, down, there is going to be a resisting force which is going to push it up. This is resistance of the medium. So this resistance force is proportional to the velocity. So faster you move, more is going to be resistance, right? It's also going to have some coefficient which depends on the structure of the liquid you have. So water is going to have one coefficient is gamma, and maybe, I don't know, like some sticky glue is going to have a different coefficient, much higher coefficient, depending on like how difficult it is to move through the media. Is going to give you different gammas. Minus means that if something is moving down, the force is going to be up, or the force is opposite direction of the velocity. How my equation is going to change? Well, it's still going to be mx second derivative, right? But on this side, this is m acceleration, right? We remember m acceleration, second derivative law. On the right side, we do have Hooke's force is still same, kx, and we do have this resistance force, and velocity is the first derivative, so I'm going to get like first derivative here. If we move everything to the left side, we are going to have standard equation, second order constant coefficient. That's what we were doing past like 3 days, right? Usually people are going to divide it by m. That's up to you. If you kind of feel you can divide it by m, because normally people like to denote this as omega square. I'm going to do division. And set somewhere that omega 0 squared equals k over m. Okay, so what are going to be the roots? Well, here we are going to have like different possibilities, right? Because we do have different numbers. Here it can be like 2 real roots, 1 multiple root, repeated root, and 2 complex roots. And all of them are going to give us slightly different motion of the mass. Well, what I'm going to do, guys, I'm going to solve this equation and just write down how the roots are going to look, okay? So characteristic equation is going to look like r squared plus gamma over m, r plus omega square equals to 0. Remember that omega is k over m, right? Well, let's just find out that's R1 and R2, right? We have gamma over m squared minus 4 omega 0 squared, the square root, plus minus gamma over m, and divided by 2. I think what I'm going to do, I'm going to take gamma over m from here in front of the root, and I'm going to write it down like this. Minus gamma over 2m, this 2 comes over here, and that's going to be 1. Well, if I take everything from here, it's going to be 1. And then it's going to be plus minus. And if I do division over here, I'm going to get something like 1 minus 4 omega 0 square. Well, I'm supposed to divide over gamma over m, and that's going to be like, imagine that I divided both terms here over gamma over m squared, took it outside, and extracted the square root after to kind of put it in front. Well, that's how solutions are going to look. Why do we need this complicated form? Well, it's going to be a little bit easier for us to decide what kind of solutions we are going to have, because initially we don't know what is gamma, what is m, and what is omega, which is defined with m and k. Now we are going to have like different situations here, right? So situation number one, under the square root, we have something positive. Gamma over m square is positive. If we have a number under the square positive, we have two real solutions. Well, I'm going to write them down. They're going to be exponential, right? So x is going to be a e to the power of r1t plus b e to the power of r2t. And what is interesting that both r1 and r2 are going to be negative. Why? r1 and r2 are less than 0. Well, because we do have this minus, right? What we have actually in parentheses, this number, no matter what is omega and gamma and m, if it's greater than 0, it's going to be subtraction from 1, right? So the whole thing is going to be less than 1. If you extract the square root, it's less than 1. If you add to 1 or subtract from 1, it's still going to be a positive number. So this one is going to give it a minus. I'm going to write it down because, sorry, of minus gamma over 2m in front of the expression. Okay, now how it's going to look on the picture? The picture is going to look like this. Well, depending, of course, of initial conditions, can look like this. Because both of them are negative, means that both exponential terms are going to be decreasing. Well, depending on like which one is decreasing faster, the faster one is going to disappear faster, and the longer one is going to give actually how fast it goes down, this one. So it's t, and this is x. Okay. So what else? Well, case number 2 is when 1 minus 4 omega 0 square over gamma over m square is less than 0. Less than 0 means that we have two complex solutions. Two complex solutions. Well, of course, I'll need to find out what is going to be our mu and our lambda, right? We do see that from this solution, our mu, our lambda is going to be lambda equals negative gamma over 2m, and mu is going to be like this square root multiplied by this, which is eventually going to give us, well, I'm just going to copy it, okay? It's going to be a square root of, I'm trying to figure out like 1 minus 4 omega 0 square over gamma over m squared. Well, we actually supposed to kind of switch them, right? Because we cannot extract a square root of a negative number. So I'm going to put minus here and plus here. So we extract the root and then multiplied by negative gamma over 2m, and that's going to be our mu. And yes, we can simplify it, but for right now, let's just label it as mu. So our solutions are going to look like x of t is e to the power of lambda t and a cosine of mu t plus b sine of mu t. What is interesting, how solution is going to look on the picture, or what kind of a solution we are going to have? Well, these two terms can be combined together the same way we did it in the undamped motion into one cosine or sine. This term means exponential kind of decrease because it's the power here is going to be negative. So we are going to have something exponential decrease due to this term. And well, depending on how we combine it to sine or to cosine and what are initial conditions, we are going to have something like this, a sinusoidal function which is oscillating with decreasing amplitude. That's why we call it damped motion, right? So you start motion with large amplitude, but steadily it's going to lose energy due to friction, and eventually it's going to stop, right? And you see that we are going to have a sinusoidal dependence, but the amplitude is changing. We are going to call mu semi-frequency. Why semi-frequency? Because, well, normally, guys, we consider periodic motion which repeats itself exactly. This one is not going to repeat itself exactly because the amplitude is changing. The period is going to stay same, but amplitude is changing, so it's not going to repeat itself exactly. So we're going to call it a semi-frequency. Well, this motion, number one, is called overdamped motion, when something just kind of tries to oscillate one time and goes to equilibrium position. Motion of type 2 is called underdamped motion. The friction is not enough to stop it right away. It's going to allow it to oscillate a little bit. We do have case 3 when we have two repeated roots, right? When actually 1 minus 4 omega is going to be equal to 0. This is called critically damped motion. And the picture for this is going to look very similar to the overdamped motion, because what we have, remember, critically damped motion is going to give you one exponential factor like C1, for example, e to the power of RT plus C2 t e to the power of RT. Again, R here is going to be negative, so there are going to be two decreasing exponents, but one of them is going to be multiplied by t. And the picture is going to look similar to what we had over here. This one, again, it's not only a possible picture, it's actually can go like this, for example. Depending on like initial conditions, the curve can look slightly different, but eventually it's going to start approaching equilibrium position. So this motion again is called critically damped, and it looks very similar to overdamped motion, no oscillations. So it's either going to look like this or going to look like that. Eventually the system will come to equilibrium position. Okay, well, what else do we need to know? Well, maybe I'll need to talk about a little bit about semi-frequency, how it's related to omega. You see that the frequency you have over here is a little bit related to omega. Actually, omega sits under the square root and kind of going to be, well, if you kind of multiply this denominator back by 1, and it's going to give you omega plus something, and this something is actually going to show you how far away it's going to be from natural frequency of undamped oscillations. Well, I think that's all. I don't want to solve any practical problems on damped motion. I think I posted 1 or 2 problems in the homework. But what you will need to do, equation is always going to look same. There's going to be no difference. You just set up correct coefficients in the equation. And if you're given initial conditions, you can calculate them using the formula. Just make sure that you kind of understand which of these 3 cases you are in. Okay, and that's going to be it about damped motion. So the next section, we are going to do actual forced vibrations. They're not going to be free anymore. But we are going to stop at this point, and I think that's going to be all. Let me see how to stop recording. Okay. Yes.